Okay, so today I am going to give lecture on the topic enzyme kinetics in front of you, and you all know that enzymes is actually biomolecules, and that biomolecules is actually made up of that are chemically enzymes are polypeptide in nature. That means that made up of large number of amino acid formation of peptide bond, as we already know all the things. And second things, as we know that if you consider functions, then this enzyme is mainly a biocatalyst. Means that works as a catalyst mostly on biochemical reaction that enhance rate of chemical reaction, rate of biochemical reaction inside and outside the living organism cell. So it must be essential that we must be know about the kinetics of enzyme. And that kinetics is almost similar as chemical kinetics. Following the chemical kinetics concept, we knowing about the rate of reaction that enhanced or generally the enzyme enhancing the rate of reaction. So that enhance or dislate the rate of reaction. So that the vary their rate of enzyme reaction. So in this chapter, this is contents we already know. Now in this chapter, it must most of the important things are active site. What is active site? So as we know that enzymes are polymer of amino acid. That means that made up of large number of amino acid, and on this, suppose if this one is an enzyme, so this enzyme has large large surface area, and at each and every place there is a specific amino acid. And here, if you see this triangle-like structure, here also amino acid is present, and that amino acid are specific. And if that are specific, that means that amino acid has their specific configuration, their specific structures, and that configurations of structures resembles with the structures of substrate. So that substrate only, and again, most of the important characteristics of enzyme is that are temperature specific. That means that shows their maximum activity at particular temperature, that is called optimum temperature. This enzyme works at a specific pH, so pH specific, works at a specific pH, optimum pH, and third one is that are most essential, that enzymes are substrate specific. Means only a specific substrate can bind with a specific enzyme during the biochemical reaction. Okay, so here you see, so at this site if you see, this is that is called the site at which substrate attached, that is called active site or substrate binding site. So you see here substrate, suppose if this one is an enzyme, this one is a substrate, this substrate a structure is analogous with this one, so that can be easily fit inside that one. That is called active site, and this active site is most important site for as far as we consider the enzymatic reaction. So now besides active site, there is a different other sites than active site is also present on the surface of enzyme, which allow to bind other molecules except substrate. So that is called allosteric site. That is most important because this allosteric site is most important for regulation of an enzyme. Okay, enzyme that regulates the enzyme activity after binding with the enzyme molecule. The site to which the effector binds is termed the allosteric site or regulatory site. Okay. Now, next things, once this enzyme and substrate comes closer, just keep in mind enzyme kinetics in your mind, concept of enzyme kinetics. We know that जो in that kind physical chemistry, we heard about different catalysts, inorganic catalyst. The same function here also, similar as your inorganic catalyst, enzyme also plays same role. Means that also catalyze the reaction. So almost the properties of inorganic catalyst and enzyme catalyst are almost same. As we said that inorganic catalyst enhancing rate of reaction by decreasing the activation energy. So activation energy is the extra energy that needed to cross the energy barrier. If you keep the transition state theory in mind, then each and every substrate can give product if once that cross the energy barrier. And the energy, extra energy needed to cross the energy barrier, that is called active. Because actually what happens, if you consider any substrate, suppose glucose. Glucose existing in nature, that means that are stable, that means that are non-reactive. But if that participate in any reaction, suppose if you try to convert that glucose in carbon dioxide and water and extract energy. So in that case what happens? In that case, once you this one activate this catalyst, and in this condition, this enzyme substrate, once that comes in contact, this enzyme and substrate bind with each other, and that substrate bind at specific site of enzyme, forming enzyme substrate complex. Due to formation of this enzyme is stable, substrate is also stable, both are stable, so that means both are non-reactive. But here we see that this substrate must converted into product. That means that substrate taking part in the reaction. So for convert this non-reactive component into reactive one, we have to increase their internal energy. Once their internal energy increase, then requirement of activation energy means height of energy barrier that decrease. We will discuss that one in next slide. Transition state theory. So simply substrate binds with enzyme at specific site, forming enzyme substrate complex. Once this enzyme, now here we can see enzyme has their own internal energy, substrate also internal energy. Now both reacting, forming enzyme substrate complex. So overall effective internal energy increases. So as this effective internal energy increase, that indicates what? So there must be activation energy requirement for crossing the energy barrier that lower down. This is the main function of enzyme. And by that way, suppose if source provide 1 kilocalorie energy per hour, and if our reaction needs 10 kilocalorie, that means that needs 10 hours. But after formation of complex, that lower down. Suppose if that lower down up to 8. So in that condition, that needs 8 hours. So time consumption that lower down. And rate of reaction is change in concentration of reactant or product per unit time. So as time decrease, time of this one production of product that decreases, rate of reaction increase. So that is the major function of substrate. So the substrate is molecule upon which an enzyme acts. Enzymes catalyze chemical reaction involving substrate. Once substrate binds to this active site, they form a complex which is intermediate complex. Intermediate enzyme substrate complex, which then produces the product and re-enzyme in their native form. That is the most important characteristics of catalyst. That may be inorganic catalyst or enzyme. So enzyme released in their native form, again the same enzyme reutilized, again that acts on another substrate and again gives the product. So this recycling, this one of enzyme is continuous process. Now hence by providing a surface for the substrate, an enzyme slows down the activation energy, means height of energy barrier, so that can easily pass the energy barrier of the reaction, and the result reaction got more easier than normal. So this is the major function, and this is the initial step when enzyme substrate interact. Next, when enzyme substrate, so this is the step as already we discussed. Step 1, combining of enzyme and the reactant forming enzyme substrate complex. Then this integration of complex molecules to the product. So enzyme release in their native form releases product. Then the whole catalyst action of enzyme is summarized as if you see the overall reaction. Then enzyme substrate interact forming enzyme substrate complex, and during that enzyme, in that enzyme substrate complex, there is some chemical changes in substrate is mainly substrate is taking place and converted into product. Finally, release enzyme in their native form and product. Now, the whole chemical kinetics is explained by this transition state theory that already we also studied in physical chemistry. So, kinetic energy of reaction proposes that reactant must collide with sufficient energy to cross the energy barrier. That already we discussed. The minimum energy that the reactant must possess to overcome this barrier is called activation energy. The transition state theory, also known as activated complex theory, considers the activation energy is the difference in energy between the reactants and an activated and transient transition intermediate. Means the total, suppose if you have two products, then internal energy of both product minus internal energy of complex. That differences is give the value of activation energy. So transition complex of the reactant possesses free energy than that of the reactant dissociate into the product. If its free energy equals or surpasses the activation energy, then reaction complete and reaction taking place in this way. So this is the basic things. We can show this one graphically. Suppose if you consider any reactant, here reactant is suppose glucose. So glucose has their own internal energy. Glucose is stable component. Glucose is non-reactive generally. So, and our target is to convert that reactant into product. So first we have to increase their first we have to convert this non-reactive one into reactive one. For that one we have to increase their internal energy degree of freedom. So so as the free energy increase, rate of collision with the substrate that increases, and if rate of collision increases, rate of production of product that also enhance. So initially, if you start with substrate glucose, then oxidation of glucose, we taking example of oxidation of glucose. So this is glucose, glucose oxidized. So this reactant has their own internal energy. This is this one. On y-axis there is an energy, and on x-axis if you take the rate of reaction coordinate. So in that case, this glucose has their some internal energy. This is this one. Now we trying to convert this reactant glucose and oxygen to carbon dioxide and water. So and this one is stable, non-reactive. So first we have to excite that. We have to excite this substrate to take part in the reaction. So initially that absorbed energy. So that absorbed energy, this red line indicates reaction without enzyme, means in absence of biocatalyst. So this reactant initially that absorb energy and reach up to this is called energy barrier. This is energy barrier. Once this one energy, internal energy of this glucose cross reach up to this point, then that able to convert into product otherwise. So initially that absorbs some amount of energy and their internal energy reach up to this point peak, that is called as this is called energy barrier, height of energy barrier. So this now slowly once that cross, then slowly that giving and releasing product. Now here without enzyme. Now in presence of enzyme, here we can see the same reactant taking part in reaction, but now in presence of enzyme. So that in presence of enzyme you can see, so the height of this point that lower down. So if this one, this is internal energy, total energy reach up to this one. So this extra energy needed by these molecules to convert into product is called activation energy. And once we add enzyme, in presence of enzyme, in presence of biocatalyst, that requirement decreases. Means activation energy, amount of activation energy required that decrease. Or you can say that height of energy barrier that decreases. As this one decrease, rate of reaction time consumption becomes lesser, and if time consumed less, then the rate of reaction that increases. So the reactant must gather energy equal to or higher than the activation energy to form that transition intermediate. And once transition into intermediate form, then that the product, otherwise not. So this is the basic concept related with your enzyme kinetics. Now this enzyme kinetics, activity of enzyme, kinetics of enzyme is explained by considering two models. Two models is given for enzyme substrate interaction, how that interact. One is Fisher's template, or also called as lock and key model, and another one is Koslett induced fit model. So first we discuss about Fisher's template or lock and key. According to this model, the active site of enzyme, where substrate bind, the active site of enzyme exists in proper conformation. Means their structure, pre-existing structure, there is no any changes we can do with that one. Their configuration of active site that remains fixed. This one. So proper conformation for catalytic even in the absence of substrate. Substrate is present or not does not matter. Their active site configuration remains fixed. As we see lock and key. So if you see lock, then specific key can insert inside that lock. The configuration of lock is created by that way so that only specific enzyme can fit. You can't operate all lock by single key. So each and every specific lock has a specific key. Similarly, here if you consider, if you consider as lock and substrate as key, so this can fit in a specific one. Similarly, as we know that substrate bind at active site, this active site is in pre-rigid form, no changes. So specific substrate comes, bind with that one. They say as in a lock, there is no option to change their configuration. That's not possible. Similarly here also. So specific key fit inside that one. Similar way, enzyme substrate complex is formed. So according to this model, the active site of enzyme exists in the proper conformation for catalytic activity even in absence of substrate. Then the active site provides by itself is a rigid precept template in which substrate fit. So fitting with size, form and groups of the substrate. So specific substrate can fit. Active site bind with substrate without any change in the former's three-dimensional structure. The substrate fitted into active site just like a key fits inside the lock. This is followed by catalytic. Then once this enzyme substrate complex form, then there is a changes, catalytic conversion of substrate into the product is taking place during that enzyme substrate complex formation. Again as product form. Now as product form, that means their configuration is not totally different from substrate. So now that their configuration is not fit with enzyme. So as either that becomes loose or very tight. So in that condition, as this one is not fitting inside the specific enzyme, so that can be released as a product form. So this model can explain the specificity of many enzymes for only of the stereoisomers can fit into the rigid three-dimensional template. This rigid template model cannot explain the change in enzyme activity. In later we will discuss about different kind of inhibition, competitive, non-competitive, uncompetitive. In that condition, it has seen that if that are in pre-rigid form, then inhibition tendency that decrease, that lesser. So mainly because that are in pre-rigid form, only specific substrate can bind. But in most of the inhibition, what happens at the place of substrate, another another substrate which is considered as inhibitor, that whose structure is almost similar as substrate, that can fit and change. So inhibit the activity of enzyme, but that is takes place when there is an flexibility, when active site are slightly flexible. So what happens if slight changes in configuration of substrate, that can fit, and enzyme can adjust themselves according to the substrate. So in that case, actual product formation rate that lower down. So this rigid template model cannot explain the change in enzyme activity in presence of some ligand called allosteric modulator, which binds to the enzyme at site other than its substrate binding site. So now this was after lock and key. Another one is Gaussian, that already we told that. So in some cases what happens, this active site has some flexibility. In lock and key, that one in pre-rigid form. But here in this model considers that that a particular enzyme active site has slight flexibility. Slight flexibility means that can adjust their configuration according to the structure of substance. That is possible here. So according to this model, the three-dimensional form of active site possesses certain degree of flexibility and does not suffer from the rigidity of fixed template. Active site does not have its fully active and complementary conformation in the absence of its substrate. Completely, as in lock and key, as we have seen, so that active site are completely substrate present or not does not matter, that remains in pre-rigid form. But here there is a slight flexibility. If there is no substrate, specific substrate, then there are chances of slight changes in configuration of active site, the possibility of there. Once substrate comes, then according to that substrate, that take the shape and fit substrate inside that. But either an approach of the substrate and initial specific superficial or loose binding with substrate, the flexible active site changes in conformation to attain the final catalytic form. The idea of such a flexible active site can explain complex saturation kinetics, competitive inhibition, allosteric mutation, and other. Now here we can see, if suppose this one is substrate, this one is an enzyme, so active, this is active. This, you can see here the shape of this active site is like this one, but shape of substrate is this one. Means if you see here, then that are not able to bind with this one. If that, as in previous case, active site was rigid, if that present here, then there is no possibility of enzyme substrate complex formation. But here, this model said that this active site has slight flexibility. So, if substrate structure is this one, then this substrate comes, and comes as this substrate comes in contact with enzyme, there is a slight changes in the configuration of enzyme is taking place. Due to slight changes in this configuration, this substrate, that means this now take configuration according to the substrate, and that is possible due to their flexible nature, flexibility. So that fit. Now after fitting this one enzyme substrate complex form, then substrate converted into product relieve enzyme in their native form. Okay, so this is two model which explain the activity of enzyme. Now as we said that the enzymes are too much specific, reaction specificity, that means that are specific, that can catalyze only specific reaction, and substrate specific that can bind with specific substrate and others. Now this model, this enzyme kinetics is mainly explained by Michaelis-Menten. Michaelis-Menten, there is a two scientists, German biochemist, who Leonard Michaelis and Canadian physician Maude Menten. These two together giving equation, and that equation explain each and every activity related with the enzyme kinetics. So Michaelis-Menten kinetics is the one of the best known models of enzyme kinetics. It is named after this one. Michaelis-Menten kinetics is model of enzyme kinetics which explain how the rate of an enzyme catalyzed reaction depends on the concentration of the enzyme and substrate. Means if you change substrate concentration, then what effect it takes place on enzyme kinetics. If enzyme concentration change, then what happens? All that things. So Michaelis-Menten given an equation for this explaining this enzyme kinetics, and that is V is equal to V or V naught, we can say. V naught or V is the initial velocity, V max maximum velocity. Means when rate of reaction reach maximum. This is substrate concentration and Km is Michaelis-Menten constant. So we have referred this one, Km is Michaelis-Menten constant, and Michaelis-Menten constant is nothing. This is the substrate concentration at which half of the maximum velocity attained. Means when initially we increase concentration of substrate, then a time comes at that substrate concentration half of the maximum, means rate of reaction becomes half of their maximum one. So that Km is the substrate concentration. So there, if that are substrate concentration, so their unit must be moles per liter. So at which the reaction velocity is 50% of Vmax, and this is the substrate concentration. Now, if you see this one from this graph, so initially when we taking some substrate, adding enzyme into that one, okay. So initially there is a no product form, so rate of reaction is 0. Slowly when we increasing substrate concentration, rate of reaction increases. Substrate concentration increase, rate of reaction increases, and after some time that reach their maximum velocity. Once that reach their maximum velocity, then it has seen that after sometimes their rate of reaction becomes constant. Why this happen? Actually, initially suppose if we start with 10 mole enzyme, okay, initially 1 mole substrate we added into that enzyme, okay. So one substrate interacting with one enzyme giving one product, suppose in 1 hour, okay. So in 1 hour rate of reaction become 1 mole per hour. Now if you increase substrate, suppose initially 1 mole, now again 1 mole if we add, then now substrate becomes 2 mole, enzyme is available in sufficient amount 10 mole. So now at a time 2 mole substrate interacting with 2 mole enzyme giving 2 mole product in 1 hour, same time. Slowly when we increasing, suppose up to 10 mole of substrate, we have 10 mole enzyme. Now if we add 10 mole of substrate, so 10 mole enzyme interacting with 10 mole substrate giving 10 mole product in 1 hour. So rate of reaction 10 mole per hour. Now after that, suppose now we adding additional 1 mole substrate again. So 10 plus 1, 11 mole. 11 mole, but here enzyme is 10 mole. So this enzyme able to convert only 10 mole of product at a time. 10 mole of substrate into product at a time. So that 10 mole enzyme interacting with 10 mole substrate giving 10 mole product in 1 hour. But so that means rate of reaction is now पहले भी था 10 मोल पर आवर, now again that are 10 मोल per hour. So rate of reaction is constant. Again 12, if you increase 12, 15, 20, then you can observe that rate of reaction remains constant. Because, why this process? Because 10 mole interacting with 10 mole substrate giving 10 mole product, enzyme release in native form. No enzyme return back and interact with substrate. So that taking another 1 hour. So rate of reaction becomes, so at a particular concentration when all the enzyme saturated with substrate, that is called saturation point. So that concentration at which all the enzyme saturate, means enzyme ability, after that enzyme ability is not possible, that no enzyme is available. So there is a no enzyme substrate complex form. So at that time, so after that, after reaching, that is called maximum velocity. That 10 mole per hour is their Vmax. Once that reach their Vmax value, now the rate of reaction becomes constant. So this is that actually explained by you. This Michaelis-Menten gave this hyperbolic form of enzyme activity. Initially, there is a no substrate. No substrate, only enzyme is no reaction. Substrate might be when starting to add substrate enzyme complex form, product formation increases and that reaches maximum up to saturation of enzyme. Once enzyme saturated, that becomes constant. So that is their maximum value. Now here you can see, if you try to explain Km values, then on x-axis there is a concentration. So at this particular concentration, here half of the maximum velocity reaches. So this half of the maximum velocity at this specific concentration, at which this half 50% reaction complete, means 50% half of the maximum velocity attained is called K. So enzyme substrate complex velocity this one. So for all enzymes that obey the Michaelis-Menten kinetics, a graph of initial velocity, rate of reaction against substrate concentration gives a rectangular hyperbola. This category of enzymes are sometimes referred to as non-allostatic enzyme. At low concentration of substrate, there is a steep increase in initially, that increase very fastly in the rate of reaction with increasing substrate concentration. As the concentration of substrate increase further, then enzyme becomes saturated with substrate. As soon as the catalytic site is empty, more substrate is available to bind and undergo reaction. Rate of formation of product now depends on activity of the enzyme itself, and adding more substrate will not affect the rate of the reaction to any significant effect. So that becomes constant. So these are the characteristics of Km values. The Michaelis-Menten constant defined as the substrate concentration at which reaction rate is half of its maximal value. And Km is expressed in moles per liter and ranges from about this one to this. Km is independent about enzyme, that do not depend upon enzyme. That depend upon nature of enzyme, but not the concentration of enzyme. But it may change by alteration of pH, because that change the properties of pH. We know that enzymes show their maximum activity, maximum characteristics at a specific optimum pH, optimum temperature, and at a specific strength of ionic concentration. Km value is used as measure of enzyme's affinity for its substrate. The lower the Km value, more tightly bound the substrate is to the, because lower means what? Substrate concentration you have to increase, then that reach to half of the, because that enzyme bound the substrate tightly. So release of product is not possible. So if product not released, then enzyme also not. So this, once that tightly bound, then their Km values lower down, and the reaction to be catalyzed and vice. So Km value also provides an idea of the strength of binding of the substrate to the enzyme molecule. So today in our lecture we discussed about these all things. In next lecture, series, we will discuss about different kinds of inhibition. Thank you.